This is Physics 2120, Lecture 28, and today we're going to finish talking about image formation. And particularly, we're going to look at different types of optical instruments. So the first optical instrument we want to talk about is a photographic camera. It consists of a light-tight chamber, a converging lens, which is going to produce a real image on the film, and the film behind the lens, which receives the image. Now, today, there's not a lot of film cameras that you see out there. A lot of them are CCD. That's all right. Where the film is, we could also put an electronic device called a CCD that will take the same picture. So, we have to get proper focusing to result in the sharpest images. And the camera is focused by changing the distance between the lens and the film. The lens-to-film distance will depend on the object distance that we're taking a picture of and the focal length of the lens. The shutter is a mechanical device that's open for only select time intervals. And that time interval that the shutter is open is called the exposure time. Light intensity is a measure of the rate at which energy is received by the film per unit area of the image. The intensity of light reaching the film is going to be proportional to the area of the lens. And the brightness of the image formed on the film depends on the light intensity. So it depends on both the focal length and the diameter of the lens. The f number of a camera lens is the ratio of focal length of the lens to its diameter. So it's f over d. The f number is often given as a description of a lens speed. A low f number is a fast lens. As the intensity of light incident on the film is related to the f number. In particular, the intensity goes like 1 over the f number squared. So on a camera, increasing the setting from one f number to the next higher value decreases the area of the aperture by a factor of 2. The lowest f number setting on a camera corresponds to the aperture being wide open and uses the maximum possible lens area. Simple cameras usually have a fixed focal length and a fixed aperture size, so that it has an f number about 11. So most cameras that have variable f numbers adjust them automatically. A high value for the f number allows for a large depth of field. That means that objects at a wide range of distances from the lens will form reasonably sharp images on the film. So the camera would not have to be focused for various objects. Now, as I said, a digital camera is similar in operation. The image doesn't form on a photographic film, it forms on a CCD, which means charge-coupled device. It digitizes the image and turns it into binary code, so that digital information can be stored on a memory chip for later retrieval. So the next optical instrument we want to talk about is just your eye. A normal eye focuses light and produces a sharp image. And the essential parts of the focusing is the cornea. It's this thin area up here where light passes through, and the aqueous humor behind the cornea. Those act as the first refracting surface of the eye. Next we have the pupil, which is a variable opening, and it's just an opening in the iris, and the iris can change the size of the pupil. It's kind of like changing the aperture in a camera. And then we have the crystalline lens. So most of the refraction takes place at the outer surface of the eye, up here where the cornea is covered with a film of tears. We can see this better if we look at a close-up of the cornea. Here we see the cornea in the light. Behind it's the aqueous humor, that clear liquid behind it, and then we see the iris here in the eyeball. So this front surface here is where most of the refraction is going to take place. So the iris is that colored portion of the eye. It's a muscular diaphragm that controls pupil size. So the iris regulates the amount of light entering the eye. It dilates the pupil in low light so that as much light can come through as possible, and it contracts the pupil in high light conditions. And the f number of your eye goes somewhere between 2.8 and 16. The cornea lens system focuses light onto the back surface of the eye. That back surface is called the retina, and it has certain cells that are sensitive receptors called rods and cones, and those structures, when they get light, sends an impulse via the optic nerve to the brain, and that's where the image is perceived. So the eye has something called accommodation, which allows it to change in the different light conditions and looking at different distances. So the eye focuses on an object by varying the shape of the pliable crystalline lens through the process. An important component is the ciliary muscle, which is situated in a circle around the rim of the lens. Thin filaments called zonules run from the muscle to the edge of the lens. So for focusing, the eye can focus, say, on a distant object, where the ciliary muscle is relaxed. And therefore the zonules tighten, and it causes the lens to flatten, increasing the focal length. For an object at infinity, the focal length of the eye is equal to that of a fixed distance between the lens and the retina, which is about 1.7 centimeters. We can also focus on nearby objects where the ciliary muscle tenses and it relaxes the zonules. The lens bulges in the middle, and the focal length decreases. And so we get the image focused on the retina. The near point is the closest distance for which the lens can accommodate to focus light on the retina. Typically, when you're around age 10, that's about 18 centimeters. The average value is about 25 meters, and it increases 25 centimeters and increases with age. It can get quite large for like 500 centimeters or greater at age 60. So I want you to find yours. What I want you to do is to either look at text or even better, take a pen or a pencil. And I want you to take that pen or pencil and I want you to hold it in front of your face and try to focus on the tip of it. And as you move it backwards and forward, find the point where you can no longer focus on the tip. That will be your near point. So hit pause for a minute and take a look and figure out what yours is. The far point of the eye represents the largest distance for which the lens of a relaxed eye can focus light on the retina. Normal vision has a far point of infinity. Now, when we're seeing colors, there's really only 3 types of color-sensitive cells in the retina. They're called red, green, and blue cones. And what color is seen depends on which cones are simulated. As you see, there's some overlap between these. This is the sensitivity to each one, and so this one is most sensitive to 420, but it'll see quite a bit further. And so by looking at the different wavelengths of light in here, different parts of the cones are stimulated, and we perceive then not just red, green, and blue, but all the other different colors. Now, there's certain conditions of the eye that we should know about. They could suffer a mismatch between the focusing power of the lens cornea system and the length of the eye. So you can be farsighted, where light rays reach the retina before they converge to form an image, or nearsighted, where a person can focus on nearby objects but not those that are far away. So farsightedness is when an object is in between your near point and your eye. It's called hyperopia. The near point of a farsighted person is much further away than the normal eye. So whereas yours might have been 18 centimeters or so, someone who's farsighted, that near point could be maybe a meter or 2 more. So if that happens, the image is going to focus behind the retina. The lens just cannot bulge enough to focus that light down correctly. So usually they can see faraway objects clearly, but not nearby ones. We can correct for farsightedness by putting a converging lens in front of the eye. The lens refracts the incoming rays a bit more towards the principal axis before entering the eye. That allows the rays to converge and focus on the retina. Nearsightedness is the opposite. It's called myopia. The far point of the nearsighted person is not infinity and may be less than 1 meter. A nearsighted person can focus on nearby objects, but not those far away. So if an object is further than their far point, they have trouble seeing because the image forms in front of the retina. We can correct for this by using a diverging lens. A diverging lens refracts the rays away from the principal axis before they enter the eye and allows the rays to focus on the retina. Other conditions of the eye include presbyopia, literally old age vision, and it's just due to a reduction in the accommodation ability. The cornea and lens essentially don't have sufficient focusing power to bring nearby objects into focus on the retina. That can be corrected using a converging lens. And then there's also astigmatism. Light from a point source produces a line image on the retina. And it's produced when either the cornea or the lens or both are not perfectly symmetric. But you can correct for an astigmatism with lenses with different curvatures in two mutually perpendicular directions. So optometrists and ophthalmologists usually prescribe lenses measured in diopters. The power, P, of a lens in diopters is equal to the inverse of the focal length in meters. So for example, a person sees clearly when he wears eyeglasses that have a power of -4 diopters and sit 2 centimeters in front of his eyes. If the person wants to switch to contact lenses, which are placed directly on the eyes, what lens power should be prescribed? So if we consider an object in infinity that's imaged at the person's far point, and plug in 1 over p plus 1 over q equals 1 over f, p is at infinity, and we know that 1 over f then would be -4 diopters. Solving for q gives us -25 centimeters. So the person's far point is 25 centimeters plus the 2 centimeters from the eye of the lens, so it's 27 centimeters from his eyes. For contact lenses then, we would want 1 over infinity plus 1 over minus 0.27 is equal to 1 over f, so it would be minus 3.7 diopters. Now, simple magnifier is an optical instrument that's just a single converging lens. It's used to increase the apparent size of an object. The size of an image formed on the retina depends on the angle subtended by the eye. So when an object is placed at the near point, the angle subtended is at a maximum. The near point, let's say, is about 25 centimeters. When the object is placed near the focal point of a converging lens, the lens forms a virtual upright enlarged image. The angular magnification is defined by little m, theta over theta naught, as the angle with the lens over the angle without the lens. The angular magnification is at a maximum when the image formed by the lens is at the near point of the eye. So q is minus 25 centimeters. We can calculate that by m max is 1 plus 25 over q. The eye is most relaxed when the image is at infinity, although the eye can focus on an object anywhere between the near point and infinity. For the image formed by a magnifying glass to appear at infinity, the object has to be at the focal point of the lens. And then the angular magnification is 25 over f. So with a single lens, it's possible to achieve angular magnifications up to about 4 without serious aberrations or blurring of the image. However, with multiple lenses, magnifications of about 20 times can be achieved. And multiple lenses can correct for aberrations. Now, a compound microscope is 2 lenses. It's going to give greater magnification than a single lens. And the objective lens is going to have a very short focal length, less than a centimeter. And the eyepiece has a focal length of only a few centimeters. The lenses are separated by a distance L. L must be bigger than either focal length. And the object is going to be placed just outside the focal point of the objective. That's going to form a real inverted image. This image is located at or close to the focal point of the eyepiece. This image acts as the object for the eyepiece, and the image seen by the eye is virtual inverted and very much enlarged. The lateral magnification by the objective is minus L over the focal length of the objective. The angular magnification by the eyepiece of the microscope is 25 over the focal length of the eyepiece. So the overall magnification of a microscope is a product of those two magnifications. which is going to be L times 25 centimeters over the product of the two focal lengths of the lenses. The ability of an optical microscope to view an object depends on the size of the object relative to the wavelength of light used to observe it. For example, you cannot observe an atom, whose diameter is approximately 0.1 nanometers, with visible light, whose wavelength is about 500 nanometers. Now, telescopes are designed to aid in viewing distant objects. There's two fundamental types of telescopes. Refracting telescopes use a combination of lenses to form an image. Reflecting telescopes use a curved mirror and a lens to form an image. Telescopes can be analyzed by considering them as two optical elements in a row. The image of the first element becomes the object of the second element. So the two lenses are arranged so that the objective forms a real inverted image of a distant object. The image is near the focal point of the eyepiece, and the two lenses are separated by distance f naught, or f objective plus f eyepiece. So the length of the tube of the telescope is equal to the sum of the two focal lengths of the lenses. The eyepiece then forms an enlarged, inverted image of the first image. The angular magnification depends on the focal lengths of the objective and eyepiece. So it's going to be the focal length of the objective over the focal length of the eyepiece. And the negative sign just means the image is inverted. Angular magnification is particularly important for observing nearby objects. Nearby objects include things like the sun or the moon. Very distant objects still are going to appear as a small point of light. Now there's some disadvantages to refracting telescopes. We need really large diameters needed to study distant objects. Large lenses are difficult and expensive to manufacture. And the weight of the large lenses leads to sagging of the tube, which is also going to bend the optical axis and is going to cause aberrations. A reflecting telescope helps overcome some of those disadvantages. We replace the objective lens with a mirror, and the mirror is often parabolic to overcome spherical aberrations. In addition, the light never passes through glass except at the eyepiece. That reduces chromatic aberrations and allows us to support the mirror and eliminates all the sagging. Now, Newton developed the first reflecting telescope. And this is a picture of what his telescope looked like. The incoming rays come down and are reflected at the mirror and appear to converge at point A. So that's where an image would form if the light was allowed to go there. But we put a small flat mirror, M, reflects that light to the opening on the side, and it goes through the eyepiece lens, and the eyepiece lens just allows you to focus it onto your retina. The largest reflecting telescope in the world is the 10-meter diameter Keck telescopes on Mauna Kea in Hawaii. And it actually has 36 hexagonally shaped computer-controlled mirrors that work together to form a large reflecting surface. The largest refracting telescope is Yerkes Observatory in Williams Bay, Wisconsin, and has a lens in the front that has a diameter of 1 meter. So today we reviewed different optical instruments, and that we can use lenses to create lots of different useful instruments. You should be familiar with the different instruments mentioned in this lecture.